all about the IEA Energy Storage Task 45. It's on large thermal energy storages. And what we are trying to do with this group of experts is to accelerate the uptake of large thermal energy storages. You all know that thermal energy storage is a key technology, especially in district heating systems. With large thermal energy storage, we can make the district heating systems more flexible. And above all, we can also enable a district heating system to become 100% renewable. So that's the background. And because the district heating systems in Europe cover a large part of all heating demand, thermal energy storage coupled to district heating systems are also supplying a large part of their services to the heating demand of EU citizens. What are we talking about? We are talking about 6 large test technologies, underground or ground-based test technologies. We have aquifer thermal energy storage that uses water layers underground. We have borehole thermal energy storage that uses the heat exchange between vertically drilled boreholes and the ground package. Then we have cavern thermal energy storage, in which caves or caverns in natural rock or in artificial constructions are being used to store heat in water. They are being flooded with water. And then old mines also can be used as large thermal energy storage, using the water in the mine and also the specific heat capacity of the surrounding rocks or soil. We have pit thermal energy storage, in which a big hole is dug into the ground and then it's filled with water. And then this water is the thermal energy storage medium. And we have the tank thermal energy storage, which is the oldest and mostly applied technology for large thermal energy storage at the moment. To give an impression of a large thermal energy storage, this is our group at the kickoff meeting that we had in Denmark 2 years ago. We are standing here in tank thermal energy storage under construction. It's only 10 meters high at the moment, but it will be 35 meters high because they start constructing first the top lid and then, jack up the construction and form the lower layers then by welding the lower plates and then lifting it up again. This tank is one of 4 tanks in Aalborg that is used for flexibility of the district heating system. And they both, or the 4 of them, all have more than 50,000 cubic meters of volume. What are we doing in the task? We subdivided the work into 4 subtasks. 2 of the subtasks you will hear more about by the presentations of Thomas and Geoffroy. These are subtask 1 on numerical simulation and subtask 4 on the improved concepts and the dissemination. And we have 2 other subtasks that will be perhaps presented in a later session of the OnSeminar, which is subtask 2 on materials database and subtask 3 on construction and performance test standards. Just a few words on these later on. What we saw is that what is needed to accelerate the uptake of large thermal energy storage systems is 4-fold. First, it's needed to raise awareness with policymakers, but also with the public, about the technologies, the processes, the permits, the procedures, and to work actively on disseminating this to the stakeholders. Then second, we should reduce the uncertainties in the process. So make people aware of the permitting process, make sure that all procedures are uniformly stated and defined. Work on standardization is very important, and also work on key performance indicators. Then we should also shorten the realization time, because nowadays the time needed from first idea to the operation of a large thermal energy storage is around 10 years, which is much too long. And then, of course, also try to decrease the costs by further development of components, by improving the processes, and also by exchanging the experience. And that's one of the things that also is being actively taken up by the Task 45. Some words on the two subtasks that will not be presented today. One is on LTES materials database and also material tests. The idea is that we create a database with material properties, especially those properties that lie outside the normal temperature and operation ranges of these materials, like with liner material to make a bit closed to water, watertight. Normally, these materials have been tested up to, say, 60 degrees centigrade, but we would also like to know what their performance is at higher temperatures. So tests for these higher temperatures need to be defined and also standardized. And then also lifetime calculation models are needed in order to already in an early stage when designing the storage, we can get a better view on the expected lifetime time of the components and the storage as a complete system. In subtask 3, we work on construction and performance check standards. Here the work is aimed at smoothening all the protocols and the procedures that are needed to plan and to design, to build and to operate large thermal energy storages. And we do this in two subtasks. One is on working on guidelines for construction and on the legal aspects. And the other one is working on guidelines for the performance assessment. And especially this latter one is very important because especially financiers and insurance companies, etc., they would like to have, I say, a well-defined and accepted procedure with which they can calculate what the value of a certain storage is and how this storage can be financed in a proper way. What are the risks and how can we calculate what these risks will mean for the total risk of the investment. That's all for now as an introduction for Task 45. What we do is we organize dissemination. Geoffroy will tell about that later. We work on the different aspects of large thermal energy storages. And we also would like to invite all those experts that are interested in more work on this to join us and to come into contact with us. Here's some links. This will be also supplied in the handouts of the presentation, and also an overview of the deliverables of the previous task. And I thank you for your attention, and let's go on with the next. Thank you.
Thank you very much, Wim. Yes, let's move directly on to Thomas.
Yes, thank you. I start sharing the screen. You should see it now in presentation mode, hopefully.
Perfect.
Yes?
Yeah.
Okay, fine. So welcome to everybody also from my side. My name is Thomas Schmidt from Solites in Germany, and I'm subtask leader of subtask 1 on numerical simulation in Task 45. And I would like to present some of the work and results from these subtasks to you today. Task 45 is a follow-up of the predecessor Task 39, and we actually in our simulation subtask we already started our work in Task 39 in 2021. At this time in a subtask C on round robin simulation, and as mentioned before, now in Task 45 in subtask 1 on numerical simulation. And our main objectives in this work are the verification of numerical simulation models for large thermal energy storages. In Task 45, we have included a second objective, and that's the provision of pre-designed tools for LTES system integration. What is our scope, Wim already introduced that we are talking about large thermal energy storage. So in task 39, we came up with a definition that you can see on the right-hand side. We are considering sensible thermal energy storage in our tasks, designed to store at least 1 gigawatt-hour heat per year and at temperatures higher than 50 degrees C, because one of our main application sectors is district heating and also industry. So that's our target temperatures. And task 39, we had an upper temperature limit of about 100 degrees. So we were mostly focusing on atmospheric storages. In task 45, this limit was increased slightly to 120 degrees. Regarding storage concepts, you have seen a similar slide from Wim already. So we are in our simulation work, we are concentrating on those 4 concepts that you can see here. So the tank thermal energy storages, both as underground and also as above ground storage, pit thermal energy storages, borehole storages, and also aquifer storages. So regarding verification or validation of numerical models, there are in general 3 different options. The first option is to compare simulation results against analytical solutions. That's, however, in most cases only possible for very simple cases and for single heat transfer aspects in our case. The second frequently used option is to compare results against experimental data. In this case, there is a rather high requirement regarding data quality, concerning accuracy and also completeness of data. And in our framework, in our application, this is often a problem that available data from existing projects don't fulfill these high requirements on data quality. And then there's a third option by comparing the simulation results against other numerical models as a benchmark. And again, in our case, as you will see soon, we have several simulation models that have been used by partners before, and many of them, or some of them at least, have been validated in the past already. A second advantage of this option is that the method is rather flexible and can be used for all storage concepts and also for various storage sizes, configurations, and applications. So for the given reasons, in task 39, we decided to go for option 3 and do our verification work based on comparing results from different numerical models with each other. In task 45, we basically continue with this approach, but in addition, we also consider one case that chooses option 2, so validation against experimental data. This table shows an overview of LTES models for different storage concepts that have been used by tasks 39 and 45 partners before. So this is not necessarily a complete list, but that's a list with models that participated in our work so far and that have been used by partners. So you can see that for all 4 storage concepts, models for different purposes are available. And if you look at the different columns, then models are mainly used for 2 different purposes. The first one is system level simulations, and the second purpose is detailed design optimizations or simulations. So regarding system simulations, this approach is an important step during project development and sizing and also selection of the proper storage concept. So it includes not only the storage itself, but also other important system level components. Whereas in the design optimization approach or models on the right-hand side, they are more suitable for more detailed investigations, for example, for complex underground situations or for non-uniform geometries or detailed design of diffuser components and things like that. So regarding system simulations, there are two simulation environments that have been used in the past frequently, and that's the software program Transys and software programs that are based on the Modelica language. So for example, Daimolar, OpenDaimolar, and there are many more. And as you can see on the table, for both system level softwares, there are a number of LTES models available meanwhile. Besides, there is also the possibility, or actually one of the partners also developed his own models in the framework MATLAB Simulink. For the comparative simulations, we developed different test cases and elaborated detailed definition of the main important aspects or the important aspects of those test cases. And this considers, for example, the LTES configuration parameters like geometry, well configuration, ball heat exchanger configuration, and so on. But also things like thermophysical properties for the storage material, for the insulation material. Also numerical parameters like discretization, far-field boundaries, simulation period, time steps, things like that have been predefined, as well as boundary conditions and model outputs that we want to use for the result comparison later on. In task 39, we developed 6 test cases as so-called stage 1 test cases. There is one test case for aquifer storage, one for borehole storage. We have 2 for pit storages with different geometries. So one is for a conical geometry, one is for a pyramidal geometry. And we also have 2 test cases for tank storages, one for an above ground solution and one for an underground solution. The second row shows the storage volumes. So you can see we are also here considering large volumes, large storages. The water-based test cases or storage concepts have volumes between 50,000 and 100,000 cubic meter. And the borehole and aquifer storages have 80,000 and close to 400,000 cubic meter. We have different storage media and also different solutions for placement of insulation and also different solutions for charging and discharging devices. In general, these stage 1 models are rather basic models regarding configuration and also regarding the operational profiles that we have selected. So in these stage 1 simulations, we have rather simple and constant profiles that consider 4 months of constant charging, 1 idle month, and then 4 months of constant discharging, followed again by 3 idle months to have 1 complete year. And storage periods then were, in most cases, 5 years. In the aquifer case, we even considered 10 years of simulation period. And for our result comparison, we took the last year of simulation. That means the 5th year for most of the test cases and the 10th year for the aquifer case. The task 39 simulations, they are already completed. You can see the participating partners in the bottom of this slide, and the numbers give an overview of participations. So in total, we had more than 40 participations in the 6 test cases with close to 30 different models. And I will present you some selected results in a minute. In task 45, we decided to define some more test cases, 11 in total. So these are the so-called stage 2 test cases. the basis of those test cases are built by the stage 1 test cases. So these base case stage 2 test cases that you can see here are more or less the same as the stage 1 test cases, with mainly one difference, and that's a more dynamic operational profile based on real operational data from existing plants. And in case of the water-based storage concepts, tank storages and pit storages, this also requires the consideration of a third diffuser layer for charging and discharging of the storage volumes. For the tank and pit storages, we furthermore decided to go for some more test cases with more specific configurations. We have, for example, for the pit storage, one test cases considering a groundwater flow, and also for the pyramidal pit storage, we have the already mentioned validation test case, where we will compare our simulation results against experimental data from a Danish plant. And also for pit and tank storages, we have 3 more test cases considering extended insulation options, or more, in these cases also insulation on sidewalls and bottom of the water volume is considered. So these test cases are still under development. The work is almost finished. 2 of the test cases are already finalized, and the others can hopefully be finished soon. So our plan is to start with the comparative simulations in task 45, within hopefully a few weeks. So in the next 3 slides, I would like to present you some exemplary results from our task 39 work, and they are all for the test case with the conical pitas. So what you can see here are results of 9 different models for yearly, the main components of the energy balance of the storage. So we have on the left-hand side the heat charged into the storage in the evaluation period, which is the 5th year of operation. The second column shows the heat discharged from the storage. The third column shows the overall thermal losses to the surroundings. And the last column shows the change in the internal energy content of the storage between the beginning of the evaluation period to the end of the evaluation period. So what we can see is that the differences between the single models is in an acceptable range of between ±2% for charging, ±3% for discharging, and ±1% for thermal losses. The only sector where we have larger relative losses of a bit more to 30% is for the change in internal energy content. But as you can see, that the absolute values are more or less 0. So this explains the large relative errors or deviations, and actually does not play a major role in the quality evaluation. So the second example shows for the same test case thermal stratification inside the water volume in 3 different times. So you can see on the y-axis the relative height of the storage. That means 1 means the top of the storage volume or the water volume, 0 means the bottom of the storage volume, and the lines show the thermal stratification, so the temperature development in the water volumes. And we have 3 specific times. The left chart shows the situation 2 months after charging. The second chart at the end of the charging period, or 4 months after the beginning of charging, and then the right diagram shows the situation after 2 months of discharging. Also, here we can see a acceptable deviation between results of different models. We have actually observed kind of a systematical deviation between two approaches for the calculation of the temperatures inside the water volume. There are some models using a so-called integral approach for this calculation, and the majority of the models are using the so-called nodal approach. And between those two approaches, there is a kind of a systematic deviation. We did some tests trying to find out more specifically the reasons for that, but we not succeeded in that so far. But as mentioned before, overall the deviations are still in an acceptable range in our opinion. Yeah, the last example shows results of the underground temperature development. These are daily values for a period of 5 years. And on this chart on the right-hand side, you can see these colored dots give the positions that we defined for the evaluation of the underground temperature field. And this chart that we can see here gives the position that is marked in this upper chart. And also here we can see that there are some small deviations, but in a very small range. So the results from this task 39 work is published already on the task 39 website. We have three different kinds of publications here. The first one is a report with model fact sheets of the models that you have seen in this overview table in the beginning of my presentation. The second set of deliverables gives a complete description and necessary input files for the presented 6 test cases of task 39. So with this information, everyone can use this test case for own calculations. And in the third part, we have all the results published. That means if somebody wants to do own calculations, all the results of the other models are available for own comparisons. Yes, to sum up, in task 39, we created 6 test cases. The works are concluded and results are available on the task 39 website. Task 45 work is ongoing, is a follow-up of the task 39 work. We have almost finished the definition of 11 additional test cases. And in addition, we are working on pre-designed tools for LT system integration in this subtask. For time reasons, it was unfortunately not possible to explain this a bit more. Yes, and last but not least, I would like to mention this European project Treasure that is on demonstration of large pit thermal energy storages. It's an ongoing project. You can see the active period here. The consortium consists of 24 partners. So we are about halfway of the project period. Many results are already available. If it's interesting for you, please have a look at the website or follow us on LinkedIn and subscribe to the newsletter. So thank you very much so far.
Thank you as well, Thomas. We can already see it's a very extensive study going on and already happened before. Many thanks. So I will go directly to the last speaker for today, and then we can conclude with the questions. Geoffroy, you're free to share your screen. And you're still silent. I'm not sure if you're aware of.
Good.
Yes.
I just lost the chat, but I managed to unmute anyway.
Perfect.
Good. But it started on the second slide, which is not what I wanted. So let's go back to the beginning. Yes. Thank you so much. Thomas has kind of stolen a bit my job, because he's already been talking about dissemination and where to find some support. But I'll do my best to still show what we're doing in terms of dissemination in task 45. and a special focus on our, let's say, rather interactive part of the dissemination in task 45. First of all, I'm Geoffroy. I work at Planenergi. We're a Danish consultancy focused on district heating and energy consultancy, renewable energy consultancy. You can see some of the projects we've worked on so far. And in this task, we're more focused on the dissemination part, but just to say that LTES implementation usually takes place in 4 main stages, which is the opportunity phase, how to determine if a project is feasible, more or less or not. Then the design phase, where more technical details are being determined for the implementation of the large thermal energy storage. Then the selected design goes into the tender phase before being implemented and operated. And this is something that has been identified in task 39, and here I'm giving you a link to find more support of what has been developed in task 39. As said previously, this task 45 is a follow-up of task 39, and we're really trying to accelerate the uptake of these storages, and dissemination is helping the general public and different actors involved with large thermal energy storages to know better the technologies that are available. In task 45, dissemination is done through 3 main activities. There is general dissemination. So this is, how to say, this is participation in conferences, art, like publishing of articles, webinars, and things like this. Then we have an activity which focuses on improved concepts of large thermal energy storages, where there we're trying to make an inventory of large thermal energy storage projects that are improving large thermal energy storage technologies. And this will be done, this will be published through reports and deliverables. And these are aimed more at technical stakeholders, but also a bit higher actors such as policymakers. And we'll be publishing the results in several chapters, starting by an overview of improved concepts, which will come out soon. And the final activity that we have in task 45 is our knowledge base. And our knowledge base, this is what I will focus on from now on in my talk. It's basically a series of webinars and Q&A sessions that are tailored to a specific audience, and that means that we're really trying to focus the content of each session to a specific audience. And after each session, our methodology is to try to have an evaluation, and then we also have an available online form for people to ask questions to our group of experts. And then from the questions and answers that occurred both during the webinars but also the Q&A sessions are being summed up on our website on a Q&A bank. And I will show you a bit how it looks like on the website afterwards. But the idea is that in task 39 and also in task 45, we have established a great group of experts that know about the different aspects of large thermal energy storages. And these experts are basically available through these webinars, Q&A sessions, and also through the Q&A form to the general public. So far the topics that have been covered by the knowledge base, and also I'm also trying to show you the topics that will be covered by the knowledge base, as I said, have been targeted towards specific actors. So in a first webinar, we've been looking at planning, legal, and societal aspects of large thermal energy storage implementation, also the financial aspects, and this is more important, let's say, for project owners, policymakers, but also the general public. In our second webinar, we are trying to focus more on technical aspects, so this is targeted more towards researchers and engineers, but also project owners. And then in our third webinar, which hasn't taken place yet, We will focus on practical experiences with large thermal energy storages. And this is actually something that came out from our surveys for evaluating the webinars and the Q&A sessions. People are demanding more concrete examples, and this is what this third webinar will focus on. We also will have a fourth webinar. This one will probably be focused more on results, actual results from the work that has been done in Task 45. And also potentially if our audience wants us to focus on a specific topic that might have been forgotten, then we will cover that as well in the last webinar. The way it looks in terms of schedule, as I've said, we've already had 2 webinars through. These are the purple ones in the top in June and December last year. We're already done with also 3 Q&A sessions, and the idea is that we're trying to have a Q&A session before and after each webinar. We started the first Q&A session after the first webinar, but we've also had a Q&A session before the second webinar and after the second webinar. And the next Q&A session will take place in May, just before the third webinar, which will be in June. And again, we've put up an online form such that you can use to ask your questions for the Q&A sessions, but also if you have general desire for information about large thermal energy storage. All the content that we are sharing from IEA Energy Storage Task 45 is published. It's published on our website, and we have both recordings of all the sessions that we do, the webinars and the Q&A sessions. We also share the presentations that are being shown. So in this webinar, you can click on each of the text here and it will give you access to the presentations from each webinar series. And then the Q&A session is being recorded, so the recordings are published, but it also gives inputs for what we call the Q&A bank. It's just a series of question and answers that you can look up on the website. And now I just wanted to give you an idea of what kind of content you will find on our website, and this is what has been discussed and shown during our 2 first webinars. This is the program from our first webinar. This, as I said earlier, focused more on legal, regulatory aspects and planning aspects of large-scale thermal energy storage implementation. And for instance, we touched upon policy framework for large thermal energy storage in the EU, as well as financing aspects. And this is just an extract of what has been presented in that webinar. Again, the recording is available and the presentations as well, but I just want to stress out this one, which was quite interesting. It focused on RED 3, which is an EU directive that is aiming to shorten the permit granting procedures for renewable energy projects, including means of storage. And this directive has explicitly mentioned large thermal energy storage in the scope, so that's why we thought it was interesting. And the framework shows or puts forward some renewable energy areas, and more specifically some renewable acceleration areas. And for those, the permitting is supposed to be accelerated, but it also needs to be implemented at national level by each EU member country. If you want to learn more about this, please have a look at the session. I will not go in depth here, but that's just a little teaser. And also to tell you that during a Q&A session after this webinar, there was actually a question asking on how efficient this RED 3 has been for large thermal energy storage. And one of the answers that came out is that it seems that the current implementation of this directive has had a limited impact for large thermal energy storage on national level. with rather low chances of accelerating permitting of large thermal energy storage projects. But maybe the next directive, RED 4, will fix this. Again, that's just a sneak peek, so please have a look at the website if you want more information. This is just to give you an overview of what the Q&A bank looks like. So if you click on a given topic, let's say planning, legal, regulatory, and social aspects, and if you want to know about legal aspects of large thermal energy storage, then this, for example, RED 3, will show up, and a summary of the answer that has been provided gives you more details about why this directive is actually limited. So again, please have a look at our website. And just to finish my presentation, I want to share this an extract of our webinar 2. And this is the program. Again, it was focused on technical aspects of large thermal energy storage. And that was, let's say, covering both all the technologies of large thermal energy storages, but also all the stages of development of large thermal energy storage. So from opportunity to implementation. And what was quite interesting, I think, at least a bit novel for the group and for the context in general, is this study from Germany. It's a national study looking at the opportunity to implement aquifer thermal energy storages coupled to district heating in Germany. It's a very common thing to do in the Netherlands, and it's been developed very much in the Netherlands, but not so much in Germany. And this study has been looking at what is the potential locational screening, let's say, and the opportunity for ATES in Germany. And this is just an extract showing how they came towards their conclusions. Again, please have a look at the recordings, and if you have any questions, we have an online formula available. So again, at the end of each of our webinars and Q&A sessions, we give the opportunity to ask questions. This is also what we will do today. And there is this online form that you can use to ask your questions to the expert group of Task 45. So feel free to use that. And last but not least, and again, I've been a bit spoiled by Thomas there, but our task is closely collaborating with other projects about large thermal energy storages. Treasure is one of them. Treasure is focusing on pit thermal energy storage, but we also have close collaboration with Users for Heat, which is looking more into ATES and BTES, and Interstores, which is looking into CTES, cavern projects, and pit thermal energy storage as well. So with this, I would like to thank you for listening, and we'll open the floor for some discussions, questions, or remarks. Thank you for listening.
Perfect. Thank you very much, Geoffroy. So I think this is a very nice way of dissemination, very, very good ways to get information, probably way more efficient than using any AI. So I only can encourage the people to talk to the expert of your task directly in this way. Okay, so if there are any questions, as I said, you can use this little hand sign you can see on the bottom of your screen very likely. And we can start maybe with the one which was in the chat already, which is for Thomas. So the question was, how did you determine what is the wetted volume of soil an ATES will interact with?
The wetted share of soil. So we more or less defined the different ground layers. We also gave the corresponding thermal thermophysical parameters, and then we defined things like well positions and flow rates for charging, discharging, and more or less these areas affected by the storage with this operational profile in the period. These are results that are that are calculated by the different models. Besides our definition of the position of the aquifer layer and of confining layers above and below. So that was part of the configuration. Yeah.
Okay.
I hope this answers the question a bit.
Thank you. Yes, I hope so too. If not, the person can feel free to ask another question or in more detail. Maybe it answered perfectly, so it's fine. Thank you. So another question in the audience or chat? Okay, so if there is no question, I might take the chance to ask the questions I wrote down. Maybe one of them. I mean, it's really nice to see how from one task to another it's developing and getting bigger, and yeah, it's very extensive. I like it a lot. My question is. I'm not really aware of which countries now are part of task 45 and have been part task at 39. But as far as I remember, there are two countries who have experience with very large thermal energy storage, and this would be Finland and China as well. Is there any connection? I think because I can imagine there are different limits, especially different climate zones or whatever, different geographic on the locations. Are they part of this work, or is there any exchange possible?
Yeah, there has been some exchange with Chinese participants, especially in the realm of pit thermal energy storage.
Yeah.
And what we would like to do is extend this the possibilities of having more information exchange between China and Europe and Northern America. And that's also because the Chinese seem to have better procedures in part to shorten the time between, say, planning and operation of storage. And that's probably something that we can learn from. Regarding the Finnish participation, there was some Finnish participation over the Interstores project. And with our last expert meeting last week, we revived that interchange again. There are some new projects also coming in Finland on large thermal energy storage. One is on pit, and the other one is on the cavern thermal energy storage. So that's really something that we are picking up now.
Okay, many thanks. Yeah, I think there's a lot to learn then from the more the better, and even if they have, if you can see that something is going quicker, it's interesting to see. Which, if the audience doesn't have another question, which would lead me to my second one, but I don't want to steal the time, so I'm happy if someone else has a question. Okay. I think you already showed so much detail, but I was curious about maybe a very general question, but you showed the different phases. Can you say which one was the one which in the moment is the most time consuming, where you think could be shortened, is the most ability to make it shorter?
Yeah, I can jump in maybe, Wim.
Yeah.
We are seeing extremely prolonged time in the opportunity phase and in the, let's say, the permitting phase. So between the opportunity phase and the tendering phase, so where you can actually start the tender and go into implementation, there's kind of a transverse phase that is the permitting phase, and this can take very long for large-scale thermal energy storage projects. It can be environmental issues, it could be a lack of regulatory framework that makes it more complicated for it to be implemented. And it's also the lack of knowledge and understanding of what these technologies can do and what they like, how they operate and how they interact with the environment, that makes this a complicated issue, I would say. And this is potentially the one that could be shortened the most, and it's very relevant in terms of the extract that I've shown from the RED 3 directive. Something like this could really help to shorten the realization time, because it kind of speeds up the process of treatment of these technologies, including large thermal energy storages. But unfortunately, it depends on how the national priorities are made. And for example, as it was said in Germany, in the example of the Q&A session that I mentioned, the renewable acceleration areas are only concerning wind, and the storage has to be located at the same position as the wind farm, which doesn't really correspond to having a use of local district heating projects. Mm-hmm. So that's what kind of blocked there. But it's a general question of permitting. I'll stop here because I see there's another question, so I'll leave time for that.
Exactly, thank you. But thanks very much. So Andy, feel free to.
Yes, I was wondering, are you seeing much interest from wind energy interests? Because it would seem to long duration heat storage would seem to have a new market for a lot of wind. We're seeing a lot of constraint in Ireland on wind. And I'm just wondering, have the wind energy, are they alert to an opportunity?
Yeah, it's a very relevant question, and what we see also in general, that the topic of sector coupling is becoming much more and more important. We see a lot of wind energy also that cannot be fed into the grid, and actually there was a new project presented at our last expert meeting in Finland, in which they say the building of the pit thermal energy storage was mostly based on using excess wind power to store the heat for seasonal storage. So that's one aspect, one, I say, movement that is now coming up more and more. Geoffroy?
Yeah, I agree with what you said, Wim. I think it's really a question of how sector coupling is prioritized in a given country. I know that in Denmark, sector coupling and power to heat are very hot topics, let's say. So therefore, we can see, for example, at the district, the Danish Association for Energy Storage, DASES, we have some actors related to the energy grid, the electricity grid, and electricity providers that are looking into storage, including thermal energy storage. But I would say that this is it's the early ages of this kind of approach. But it would only make more sense with time. All countries that are putting new targets for their energy sector these days are talking about electrification. So the best way to store large amounts of energy at an effective cost is these large thermal energy storages. So this will come, but for now there is no. It's only the beginning of this era, I would say, and that kind of justifies the potential of these technologies to help the sector. But it also requires a development of district heating, and that's not something that all countries are able to understand.
Okay, thank you very much. Oh, so yeah.
I can maybe also add from the German perspective. There is this general interest and increasing interest in the sector coupling topic in general. And we have since a number of years we have contact to a wind park creator and operator in the north of Germany that asked us to do some 2 feasibility studies for using dispatch or avoiding dispatch of wind electricity, and instead using it by storing it in large storages and supplying district heating networks in the rural area. So there's a concrete and specific interest in two or three projects.
Okay, thank you very much. I hope, Andy, your question is answered. If not, you can stay in contact. Okay, perfect.
No, that's interesting, because we had something like 25% curtailment in the north of Ireland in 24, and we want to add more wind, so we can see more and more spare wind energy coming onto systems. And also, I noticed that we have more wind in winter, so perhaps the storage wouldn't have to be very large, or it could serve a bigger town. Yep.
It sounds like a very interesting use case to me.
Yeah.
A good opportunity. So looking at the time, we have one more question. I would say this would be the last one. And the rest, maybe if there would be questions after this one, we can you can exchange the email addresses, or you can write the Q&A possibility. But the one question we have is, have you seen linking of data centers with large thermal energy storages?
I can take this one. There is not currently, I don't know of a project that has been doing, as Andy was mentioning, like a direct connection between a data center and a large thermal energy storage built together, let's say, in an integrated way, and also offering services for the grid in this way. But we already see some data centers having their waste heats reused for district heating. And that requires large thermal energy storage, because a data center will not produce necessarily when you have the heat demand corresponding. So in order to do that properly, you need a heat pump, and also a heat pump will function better if it's connected to a large thermal energy storage. At this point, it's mostly tank thermal energy storages that are being used, but as data centers are growing and are getting bigger, I think even larger storages could be considered. So pit thermal energy storage, maybe even aquifer thermal energy storage for more seasonal storage of this kind of heat.
Thank you. So Thomas.
There is one project or plant where a borehole storage is directly connected to a data center at the University of Darmstadt, and the stored heat is then used via heat pump to feed into the university district heating network again in wintertime. So, but that's the only one with a direct coupling that I know.